Alright, before watching this video, make sure you try this clicker question on your own. Alright, here we have object A is attached to spring A and is moving in simple harmonic motion. Object B is attached to spring B and is moving in simple harmonic motion. The period and the amplitude of object B are both 2 times the corresponding values of object A. So what we're being told is, here's object A, and it's attached to spring A. Here's object B attached to spring B. The period and the amplitude of object B are 2 times the corresponding values. So period of B is 2 times period of A. Amplitude of B is 2 times amplitude of A. They want us to compare the maximum speeds of the 2 objects. Well, we know V max goes as omega A. So V max A is equal to omega A times amplitude of A. And we know the relationship from omega to period is the following. So omega is 2 pi divided by the period. So I can rewrite this as V max A is equal to 2 pi amplitude of, oops, that should have been an A, amplitude of A divided by period of A. And then similarly, the maximum speed for object B is going to be 2 pi amplitude of B divided by period of B. Well, what we know is that both the amplitude of B is doubled from A and the period for B is doubled from A. So each of these, so let's write that in, is V max B is 2 pi, 2 times amplitude for A divided by 2 times period for A. Well, the factors of 2 cancel out, and if you compare V max A, it's exactly equal to V max B. So the fact that the amplitude is doubled and the period is doubled, that overall ends up canceling out the effect it would have on the max speed. So the maximum speed of object A is the same as the max speed of object B. By the way, if you have any questions about the problems that we're going through here, please do come to office hours and clarify those. Okay, now here's the very last example for this lecture. When a mass undergoes simple harmonic motion, when a mass undergoing simple harmonic motion is 12 centimeters away from the equilibrium position, its kinetic energy is 3 joules, its elastic potential energy is 1 joules. What is the amplitude of oscillations? So let's write down our given information. So when x is 12 centimeters away from the equilibrium, our kinetic energy, Ke, is 3 joules. And then our potential energy at that point is 1 joules. Well, that tells us that our total energy is 4 joules. And we want to find the amplitude of oscillation. Well, what might be useful is to compare. So here's the equilibrium, and they're telling us when we're 12 centimeters away from the equilibrium. So here's 12 centimeters. We know that the Ke is 3 joules, and we know the potential energy is 1 joule. So let's go ahead and compare this point to the maximum amplitude. So let's say the max amplitude A is somewhere over here. Because we know at this point, all we have is spring potential energy, and that's equal to 1/2 Ka squared. So we know that 1/2 Ka squared, which is the total energy, is equal to 4 joules. We also know that the spring potential energy here is 1/2 Kx squared, which is equal to 1 joule. Now here you have 2 equations and 2 unknowns. We don't necessarily know K, and we don't know the amplitude, but we know where, for what x, this is equal to 1 joule. So we can just go ahead and solve for A in this case. And one quick way of solving these equations is divide the 2 equations by each other. So if we divide these 2 equations, the factors of 1/2 and K cancel, and you get A squared over x squared is equal to 4. That means A is equal to square root 4, which is just 2 times x. So twice x is 24, because x is, we know it was pulled at 12 centimeters. So 2 times 12 centimeters gives us that the amplitude of this thing is 24 centimeters. There's a few different ways of approaching this. So if you have a different approach for this problem, please try that and make sure you can get to the correct result. All right, that's it for, oh, no, there's one more question. The last question here is we have a pendulum setup that has a period of 1 second on Earth. What is the period on the moon, where G is this? So they don't tell us that this is a physical pendulum, because if this were a physical pendulum, they'd have to give us its mass, its moment of inertia, and other things. So let's just start with the fact that the period of a pendulum is root, oh, actually, I remember the frequency of the pendulum is root G over L. That means the period will be 2 pi root L over G. And if you ever forget, you can at least check the units. So, I mean, you'll have this written on your equation sheet, but let's just check units real quick. G is in meters per second squared. Length is in meters, and we have a square root of the entire thing. So we know the meters are going to end up canceling out, and this gives us overall 1 over seconds, which makes sense because frequency is in radians per second. So, and radians aren't coming out of these units. Radians are just units of measure for angle. So this has the correct units, and you can do a similar thing here with time. You know, length is in meters, G is in meters per second squared, and there's a square root of the whole thing, and this is going to, in fact, give us seconds. Okay, back to the problem. We know that the period on Earth is so T Earth is length on Earth, G on Earth. Well, the length is independent on where you are. The length of the pendulum, it is whatever it is, so that's just L. Now the period on the moon is going to be 2 pi square root of L over G moon. And we know G on moon is 1/6 G Earth. So when we plug that in, we get 2 pi square root of L. So if I do G over 6 on the bottom, that's G Earth with a 6 on top. So that basically gives me an overall factor of square root of 6 times 2 pi square root of L over G Earth. Well, we know from the problem that this is equal to 1 second. So this whole thing is 1 second. We need to multiply by a root 6. All right, let's see what we get when we multiply 1 by square root of 6. You know, square root of 6 is somewhere between 2 and 3, because 2 squared is 4, 3 squared is 9. So you can approximate it, or you just plug in square root of 6 in your calculator and get that this is approximately 2.4 seconds or 2.5 seconds. All right. Okay, now that's the end of all the examples. I have a couple slides here on damped oscillators, which is optional material for you to read about, and there's a whole section, very interesting section in the book that you can read about it, or if you want to talk more about this, you're welcome to come to office hours and we can talk about damped oscillations.